We've been looking at using a derivative to find out when a function is increasing or decreasing. What about those spots where it changes from increasing to decreasing? More specifically, where the derivative is zero. So if f is a function and x sub 0 is a point in the domain of that function, we say that x sub 0 is a stationary point of f if f prime of x sub 0 equals 0. Or in other words, the tangent line is horizontal at that point. If f is a function and x sub 0 is a point in its domain, just like before, x sub 0 we call a critical point if the derivative is 0 or it's not defined at that point. So if you notice, critical point is more an all-encompassing definition. So a stationary point is a critical point, but not every critical point is a stationary point. Let's see what I mean by that. If we look at the absolute value of x graph, at x equals 0, the derivative is not defined. So that's a critical point, but it's not a stationary point because f prime of 0 is not defined there. On the other hand, if we look at the parabola y equals x squared at 0, 0 at the origin, that's a critical point and it's a stationary point. So anything that's a stationary point is by definition a critical point, but not every critical point is a stationary point. So whenever you have sharp corners or cusps on a graph where the derivative is not defined, we call that a critical point, but it's not a stationary point. All right, let's take a look at some examples. If a function has a local minimum or maximum at x equal a, then the derivative is 0, or f prime of a is not defined. So don't think the inverse of that statement is necessarily true. Just because the derivative is 0, that doesn't mean we have a local minimum or local maximum. We may, or we may not. We're going to have to do some more investigation to see. So like I said, let's look at a couple examples. Find all the local extremum for this function. So the first thing we want to do is find where are the stationary points. So we're going to find the derivative, and then we're going to set it equal to 0. So f prime of x is 3x squared minus 6x minus 9. We'll set that equal to 0. I can factor out a 3. And then I'll be left with an x squared minus 2x minus 3, which I can factor into two binomials as x minus 3, x plus 1. So therefore, we have stationary points at x equals 3 and x equals negative 1. So what we're going to do with that is we're going to make a plus minus chart or a sign chart for the derivative. So it's kind of like a number line, and I want to put these two important values, negative 1, positive 3, and normally on a number line we write the values underneath. Here I'm going to write the x values on top, and underneath I'm going to write the sign of f prime. So we know that f prime is equal to 0 when x is those two values. And it's not equal to 0 anywhere else. So these two values of x split this into three sections. Numbers between negative 1 and 3, numbers greater than 3 to infinity, and smaller than negative 1 to negative infinity. In each of these sections, f prime is either going to be entirely positive or entirely negative. But it's not going to have both positive and negative values when x is less than negative 1. Because if it did, then there'd have to be another 0 separating those positive and negative values of f prime. So all I need to do is pick one value of x that's less than negative 1 and evaluate it for my derivative. And if it's a positive value, that means everything in this interval is positive. Or if it's a negative value, everything will be negative. And likewise, I'm going to check each of these intervals. So let's start with this. Let's let x equal, negative 2. Now if I plug negative 2 into my derivative, and usually I think it's easier to plug it into the factored form, because I really don't care about the specific value I'm going to get for f prime. I just want to know, is it going to be positive or is it going to be negative? So if I plug in a negative 2 for x, this parentheses here is going to be a negative value. This is also going to be a negative value. And then when I multiply a negative times a negative times 3, I'm going to get a positive answer. So I know that f prime is always going to be positive when x is less than negative 1. Now I'm going to move to this interval. Let's pick a number between negative 1 and 3. I don't know, 0 would be easy. If I plug in 0 to my derivative, I'm going to get a negative value, a positive value, and when I multiply these, a negative times a positive is a negative, so I know that f prime is going to be negative for any x value between negative 1 and 3. And then finally, let's get this last section here. When x is greater than 3, let's pick, 4. If I plug in 4 to my derivative, this is going to be a positive amount. That'll be positive. So when I multiply, I'm going to get a positive answer. And by the way, don't think that this will always alternate. A lot of times it will, but not always. All right, so this tells me since f prime is positive, I know my function f is increasing, and then it levels off, and then it's decreasing. That tells me that at this value, when x is negative 1 and my derivative is 0, I have a local maximum. Because the derivative told me, since f prime was positive, f is increasing, and then it levels off, and then it decreases. So in other words, it's increasing, it levels off, and then it's decreasing. So right there I have a local maximum. And I can spell that better. Local max. All right, let's look around in the next 0. Since f prime is negative, my function f is decreasing, then it levels off, and then it's increasing. So that tells me that I have a local minimum. So another way of thinking about this is the signs of our derivatives were positive, and then 0, and then negative, and then 0, and then positive. So that gives me the general shape of my graph. And then I know that this is at x equals negative 1, and this is at x equals positive 3. So if I make a little chart here, so we have local max at x equals negative 1, and the maximum value, and that's when I plug in negative 1, not into my derivative, because I know it's going to be 0, it's when I plug it back into f. So when I evaluate f at x equals negative 1, that will give me my output. And so that's going to give me, what, a negative 1 minus 3 plus 9 plus 5. So negative 4, so I believe that's 10, right? So in other words, I have a local max at negative 1 comma 10. So sometimes the questions are worded a little differently. So if it says, where is the local maximum, you would say at x equals negative 1. If they said, what's the maximum value, you would say 10. If it just says find the local max, you would probably just write the coordinates negative 1, 10. All right, and then we'll do the same thing for the local minimum. That occurs at x equals 3. And then the minimum value, if I plug 3 into my original function, f of 3, what are we going to get there? We're going to get 27 minus 27, that's convenient. And then negative 27 plus 5 is a negative 22. So 3 comma negative 22 is my local minimum. And so that's how we use the derivative and finding these stationary points to help us find the local extremum. Let's look at another example. find all the local extremum for this function. This might be a good time to hit pause and try this on your own and then come back and compare. All right, so we're going to calculate the derivative, set it equal to 0. 3x squared minus 12x plus 12. Similar idea, factor out a 3 from all these. I'll have x squared minus 4x plus 4. I can factor that to x minus 2, x minus 2. So I only have one stationary point, and that's at x equals 2, which is also a critical point. And so now what I want to do is find out what's happening at x equal 2. Is it a local minimum, a local maximum? So I'm going to make my sign chart, my x values, my g prime values. X equals 2. We know g prime is 0 at that value. So let's pick a number less than 2. Lost my arrow, draw another arrow. So we're going to pick a number less than 2, plug it into g prime. So I don't know, how about 0? When I plug 0 in to g prime, I'm going to get 12, positive number. Let's keep the colors coordinated here, positive. All right, now let's pick a number bigger than 2, like, I don't know, 4. When I plug that in, I'm going to get a positive times a positive times 3 is a positive. So I get positive. So what's going on with my graph? G prime is positive, so G is increasing, and then it levels off, and then it increases again. So the graph of G is increasing, levels off, and then increases again. So as you can see, we have a stationary point right here, but it's not a local minimum or a local maximum. So we have no local min or max. But we do have this special point here. And so how should we refer to that, or what should we say about it? Well, that's what we refer to as a stationary inflection point. A stationary inflection point. And that's when it's the first derivative is 0, but we don't have a local minimum or a local maximum. So basically it just means that there's a horizontal tangent line at that point, but it's not a local min or max. So just because the derivative is 0 doesn't mean that it's going to be a maximum or a minimum. All right, let's look at one last example. And once again, you might want to pause, try this, see what you got. Find the maximum and minimum values of this graph on the interval -3 to 5. Okay, well, we know what an x cubed graph looks like. You know, in general, it might look something like this. Or I guess it could just look like that. But right now, we're saying over a certain interval. So there's 1. And then we have another one. Like that. Okay, so now, you know, normally, if we didn't have any restrictions, we'd say, okay, we have a local maximum here, and we have a local minimum here, and there's no global minimum or global maximum because they go up and down forever, positive infinity, negative infinity. But once we put some restrictions on them, like this, well, now we might have a maximum value right here. Because notice that that's higher than the local max that I have in red. On the other hand, if maybe our interval looks like that, now that's not the maximum value of my function. The maximum value of my function is there at the local max. Similarly, we could have a minimum value on that interval, which would be at the endpoint, or depending on, you know, where my interval is at, let's say here, now that's not a minimum value, there's the minimum value. So what do we need to do? Well, first of all, we need to find all the local minimums and maximums. And we need to see if those fall within this interval. And so those could be possibilities. On the other hand, we also need to check the endpoints of this interval and see what our function values are there. And those might be more or less than our local maxes and mins. So first thing we're going to do is let's find all the stationary points. So let's find y prime and we'll set it equal to 0. So we have 3x squared minus 12x. Set that equal to 0. We can factor out a 3x. And we're left with x minus 4. Either 3x is equal to 0, which means x equals 0, or x is equal to 4. So let's make a sign chart and see what's going on. So we have 0, and we have 4, we have x, and we have y prime. It's important to label these sign charts, by the way, because later on when we start looking at second derivatives, and that'll tell us about the concavity of our graphs, we're going to be making sign charts for those as well. So when you're looking at a sign chart, you want to know exactly what it's referring to. All right, so these are stationary points. The derivative is 0. Now let's check some values. So let's say when x is less than 0, how about negative 1? If I plug in a negative 1 here, I'm going to get a negative times a negative is a positive. So y prime is positive, which tells me that my graph is increasing. And then let's pick a number between 0 and 4. How about 1? That's positive, that's negative. Positive times a negative is a negative. That tells me my graph of y is going to be decreasing. That's going down. And then bigger than 4, how about 5? Positive, positive, multiply gives me a positive. Okay, so if y prime is positive, that means y is increasing. It levels off, then it's decreasing, then it levels off, and then it's increasing. Pretty much like my picture here. So this is going to be a local maximum at x equals 0. And this one will be a local minimum. So the next thing we need to do is find out what are the values of my function at those points. So let's see, when x is 0, if I plug in 0 here, I'm going to get y is equal to 5. That's a local maximum. And then when x is 4, and I plug 4 in, I'm going to get, what am I going to get? I'm going to get 4 cubed is 64, minus 4 squared is 16 times 6 is 96, plus 5. So that's a negative 32, negative 27, I think. Verify at home. Okay. So, and that's a local minimum, so negative 27 might be my minimum on this interval, but now I need to check the endpoints. So first let's check at negative 3. When I plug in negative 3 into my function, I'm going to get negative 27. That's minus 54 plus 5. So that's going to give me, what, negative 76? Wow, so that's a lot smaller than negative 27. So this is going to be my minimum over that entire interval. And then I'm also going to check 5. And if I plug 5 in, I'm going to get 5 cubed, 125, minus 6 times 25 is about 50, plus 5. So what does that give me? Negative 25 plus 5, negative 20. And so the greatest value I have occurs at 0.5. So this is my maximum. So notice that my local max wound up being the global max. So in terms of this picture, let me erase some of this stuff here, get this out of the way. Here. Okay, in terms of the picture, it was probably more like this, and oops, and something like that. So therefore, at this endpoint, I had my minimum, a value of negative 76. And at this point, I had my maximum value of 5. And then at this end point, that wasn't more, that was only a negative 20, which is less than positive 5. So that was lower than that. This local minimum, negative 27, that wasn't as low as this endpoint. So those are my two answers for this. So when it's on a closed interval, you have to check the endpoints. Okay. So practicing a few, you'll get better at this. Section 13D, and it starts on page 328.